Hello everyone, welcome to the second lecture of the NPTEL course on simulation of modern power systems, wherein we continue with the introduction part, and precisely we will talk about basic circuit analysis, to be precise nodal and mesh analysis which are based on Kirchhoff's voltage and current laws. And we'll see, try to understand that if this circuit analysis, which essentially involves solving certain simultaneous linear equations for a given DC network, AC network, be it in time domain or phasor domain, why the same circuit analysis is still not used for a given practical modern power network. We'll see that in detail in this discussion. The previous lecture, we have talked about the evolution of power systems, how AC networks came in, DC networks came in, what are the recent issues and challenges involved in operation, protection and control of power networks, and the different types of analysis that comes in for analyzing this given power network under different time frames, steady state versus transient versus subtransient, and finally the ultra fast transient analysis. So, circuit analysis, as we all understand, our given power network is one of the most complex man-made network having several interconnected elements, electrical elements, which start all the way from generators to step-up transformers. Then we have transmission lines, which form our conductors. Then we have step-down transformers followed by distribution lines, and eventually we have these loads from where the power flows from generation into the load. And if the load also has its own generation capability in terms of renewable energy resources, then there is also a possibility of bidirectional flow of power from the load end to the transmission end, and from there the power gets distributed across different distribution and subtransmission networks. So, if the idea is this, that our power network has all these electrical components, then given this electrical circuit which has all these different components, wherein we know the corresponding parameters. By parameters I mean the distribution line resistance, inductance, transmission line resistance, inductance, capacitance, the values of step down transformers in terms of their turn ratios, and the topology in the way that how these different elements are interconnected among themselves, whether they are connected in series, in parallel, star, delta configuration. And assuming that these sources, the generators and the loads, they are being represented by certain voltage or current sources, circuit analysis essentially aids in letting us know the voltages and currents in remaining part of the circuit at remaining nodes where a dedicated generator or voltage is not connected, at remaining branches where there is a resistance present, probably let's say a transmission line. And all this can be obtained by using the circuit analysis principle, which often results into a set of linear equations, which if we solve, we get to know the corresponding unknown voltages and currents. So, I'll take an example of nodal analysis. I'm sure all of us are very well aware of what nodal analysis is. The term nodal analysis or node comes from the definition of node in a given electrical circuit. Here I have a given electrical circuit wherein I can easily identify that there are 5 nodes. To be precise, a node in an electrical circuit is a point of interconnection where at least 2 different circuit elements or more than 2 circuit elements are directly connected among each other. That means if I have to talk about or identify the nodes, then it's very easy that I have node A, node B, node C, D and E. If I know these 5 different nodes, the remaining other branches are also well defined because the corresponding parameters and the way these are connected, their topology is also known. And in this circuit, I have also been given 2 voltage sources. One is a 10 volt DC source, the other is a 5 volt DC source. And the idea is to find the node voltages across nodes A, B, C, D and E, and that's where VA, VB, VC, VD, VE, the corresponding potentials of these nodes are coming in. And since there are 5 nodes, our aim is to find these 5 voltages. If we know these 5 voltages, then we can very easily apply KVL across any 2 nodes and probably also find the corresponding currents through these circuit elements or the branches. Having said that, this is a circuit where there are 5 nodes, and we all have to remember or note that current in a circuit flows through the circuit, so it's generally associated with a series interpretation, whereas voltage or potential is across a circuit, and hence it is generally associated with a parallel interpretation. Now, when we say that we have to find these 5 voltages, and voltages do come from the term potential, to be precise, potential differences, then what is the reference for these 5 voltages? What is the value compared to which these nodes have their potentials? Since voltage is always a relative quantity with respect to a reference, so among these 5 nodes, given any network, we'll have to first assume our ground potential or zero potential. If it is not given, then also we will have to inherently, assuming that one of our nodes is at ground or zero potential, only then I will be able to find the remaining voltages, because all these have to be measured with respect to some reference. So if I choose node E as the reference node, which is just for the sake of simplicity, although for the case of nodal analysis, you can choose any of those voltages, remaining 4 voltages as the reference node, your overall numbers or solutions will remain the same in terms of power consumption, power generation, and the current directions, the current flows. The absolute voltage values, they may have change in directions, change in signs or so on, but the overall currents and power flows, they will remain the same. The potential differences between 2 nodes, it will also remain the same even if you change the reference node from node E to any of A, B, C, D potentials. Given that node E is the reference, we can easily apply KVL across this branch, and we would see that if we apply KVL, we start from this node, which is VE. We reach the negative potential of the DC source. From negative to positive, there is a gain in voltage, so we have plus 10 volt. And eventually we reach node A, where the voltage is VA. Since VE is chosen as 0 for reference, so hence we easily get VA as 10 volt just by KVL application. And then we are left with 3 other voltages, which are VB, VC, and VD. Coincidentally, nodes B and C, they form a super node. And so what is the definition of super node? A definition of super node is that we identify the 2 nodes across which the known voltage source is predefined. If we know the potential of node C, and since 5 volt is connected between B and C, automatically voltage of node B gets defined. So we don't have to have 2 different equations, 2 different analyses for finding separate values of B and C. B and C, since they form a super node, their potentials are predefined in itself, and hence we call B and C to be a super node. The same definition if I apply for nodes A and B, the difference between potentials of node A and node B depends on the current which is flowing through the 2 ohm resistor. Until and unless I know what is this current, I will not be able to find VA in terms of VB. And to find current, I have to find VA and VB in itself. So it's a cyclic process, or problem gets entangled into a cyclic process. On the other hand, if I see super nodes, C, if it is known, B will automatically be known because 5 volt is predefined, and that's where the definition of super node comes in. Across super node, we apply KVL, and hence we get one equation. We have VD also as another unknown. We have 3 unknowns, so we need at least 3 equations. So how do we find the other equation? We apply KCL at node B, and also apply KCL at node D. I think this has to be B and C. So B and C, since they form a super nodes, we apply KCL at node B. KCL at node B gives VA minus VB, which is the current through the 2 ohm resistor. And if this is the incoming current, the outgoing current is VB by 8, which is this term. And then eventually we have VC minus VD by 1 ohm, which is the current flowing on this 1 ohm resistor. Why can't we write the current through 1 ohm resistor in terms of VB and VD? The answer lies to that question in terms of the definition of supernode. VB dictates what is VC, and then from VC we get in terms of VD, and that's how we get the corresponding current. Similarly, if we apply KCL at node D, we get the corresponding voltages. Since now we have got 3 equations, 1, 2 and 3, we can solve these simultaneous equations to get our final voltages. From the voltages, we can again apply KVL and find the corresponding currents. These currents, they may fall in place depending on the assumption of current direction that we chose in the initial analysis. So if we strictly see, the final current that we are getting here is 0.6 amperes from node D to node C. So alternatively, if we find Vc minus Vd by 1 ohm, which is as per from this number, then this is clearly minus 0.60 ampere, which means that the KCL application of writing this equation was in a wrong direction. The direction was just wrong, and this negative number here indicates that we have to reverse the current direction, and that's where 0.6 ampere current comes in. Often students, they find this direction of current to be little difficult, but as long as you stick to the direction of currents that you have assumed, the corresponding plus and minus numbers, they inherently take care of those directions. If the direction of current assumed is in from left to right and the value of the current turns out to be 0.2 ampere, that means your direction was inherently correct. If you assume the direction of current from left to right, but the current from the analysis comes out to be 0.2 ampere negative, it would mean that your direction choice was wrong. The value remains the same, but the current direction just reverses. So that's about nodal analysis. The same also goes well for the mesh analysis part. In fact, nodal analysis and mesh analysis are sort of complementary or supplementary concepts to each other. In node analysis, we first try to find the node voltages and then we try to find the corresponding branch currents. In mesh analysis, the objective is to find the branch currents or mesh currents first and then try to arrive at the node voltages. Both do involve application of KCL and KVL, but the priority to use of KVL in mesh analysis gives the mesh part, whereas in nodal we try to more use KCL and later on we use KVLs. So in this given circuit, it's a AC phasor circuit because our voltages are defined in terms of phasors. Current is also phasors. This is an independent ideal voltage source. This is an independent ideal current source. And over here we have a dependent current source, and here we have a current dependent voltage source. This is a current dependent current source. This one is a current dependent voltage source. And overall objective is to find the 4 mesh currents. This circuit, if we identify the 4 meshes, mesh is basically a branch or loop in a circuit. If we identify those unique meshes and then we superimpose all those meshes, our circuit remains unchanged. It is defined in the least minimum number of meshes. So in this given circuit, we can easily see we have 4 unique meshes. And if we assume that these 4 unique meshes have their respective currents I1, I2, I3, again just based on direction assumption, these current directions may be different, which our numbers will eventually take care of. So if you assume these 4 meshes having these currents, then it is clear to see that in mesh 2, since we have a 6 ampere independent current source present in mesh 2, so I2, which is flowing through 10 ohms, then through this current source and again coming back from here, it cannot be different from 6 ampere because as I mentioned, current is generally interpreted as a series entity. So in a given circuit, in a series combination, 2 currents cannot be different as long as both are either the same or both are either different. So if we are assuming I2 to be the current in this mesh, then it has to be same as the 6 ampere current. So we get I2 here. Then we have I3, I4 and I1. We have 3 unknowns. We need 3 equations. So if we apply current or KCL difference across node A and B, we see I0 is I2 minus I3, which is 6 minus I3. And meshes 3 and 4 here, they form a super mesh. But before I go there, we apply KCL at node B. We get a corresponding current equation. Meshes 3 and 4, they form a super mesh. Why is that? The reason why I3 and I4 currents meshes form a super mesh, because in between them there is a current dependent current source, which indicates that if I3 is the incoming current through this element and I4 is the outgoing current, since 2I0 is the current which is flowing through this current dependent current source, it has to be equal to I3 and I4. That means if I know what is I3, I can easily get to know what is I4, provided I know what is I0. We have already defined I0 in terms of 6 and I3. So in a way, I3 and I4 become very strongly dependent among each other. If we know one current, the other current gets known. The same is the idea as we defined for super node. We apply KVL across this super mesh, and then we get our fifth equation. Solving equations 4 and 5, we get I3 and I4. We come back to KVL in mesh 1, wherein we only have I1 as the unknown current. We solve this and we get the I1 current. Since we have got all our individual currents, we can then find the corresponding voltage drops across these elements, find their corresponding power consumptions, and then verify it that whatever power is being consumed, be it real or reactive power in these different capacitors, inductors, RL load, resistive load, whatever power is being consumed, be it real or reactive, all that is coming from the combinations of the independent voltage source, independent current source, current dependent current source, and current dependent voltage source. So power checks or balances can be maintained or ensured. So coming back to the question that we have had in the beginning of this lecture is, having understood this simple linear analysis, which is very easy for the human mind to interpret, appreciate, often it is interesting to solve these linear equations. Why can't the same be done for a given power network? Yes, it can very well easily be done. If that is so, then why is it not discussed the way we are discussing in the current discussion as it is present in the books? Why do we have to understand power flow analysis or PF analysis? The answer to that question lies in the fact that how our sources are actually defined. In all this mesh or the nodal analysis that we saw, our sources were defined in terms of voltages, currents, or functions of currents or voltages. Nowhere in nodal or mesh analysis our sources were defined in terms of powers. In practice, in reality, any generator, transformer, load we take, be it the case of this light load that we have in this room, if we check its nameplate rating, the first rating that comes often is the power that it is going to consume, the voltage at which it is supposed to operate, and from there you can correspondingly find the corresponding current at which it will operate. If it is supplied rated voltage, then it would consume rated power, and for rated power it would consume the corresponding rated current. The generators that we operate, the thermal plants, hydro plants, their designing specifications again come from the perspective of real and reactive powers. The sources are specified, that's why in terms of powers, and not often in terms of currents and voltages. If our sources are in terms of powers, and given that we are talking about simulation of modern power analysis, we all know that power is essentially a product of voltage and current, where voltage is the voltage across the element, current is the current through the element, then the corresponding power can be evaluated by this product. If power is known, because that's how our sources are defined, the corresponding circuit analysis, where the objective is to find these voltage and currents, would result no more to linear equations. We will have equations where we would have products of two terms, and essentially it becomes a nonlinear equation. And hence, even though KCL, KVL is true, the resulting analysis will no more remain linear because of this product of voltage and current. And hence, that's the reason why we have nonlinear equations, and that's where precisely we need a different mindset, we need a different understanding. The first module that we will talk, which is power flow analysis, will essentially help us understand how to solve these nonlinear equations for a given interconnected power network, where the bus or the nodes, their injections or powers are known, at least some buses and some nodes, their powers are known. The network parameters are known, that means the line resistances, inductances, capacitance are known. The network topology is known, how many parallel circuits, series circuits do we have, that is known. And for the same circuit, the way we did or understood circuit analysis, the same principle if it is applied, the overall equation that we would get there would be nonlinear equations. Power flow analysis is basically an understanding of how to obtain these nonlinear equations and how do we solve them so that we get our bus voltages or node voltages. And since we are talking about AC networks, so we will have phasor domain representation where every voltage will have its magnitude as well as a phase angle, as we saw for the case of this 24 at an angle 0 voltage source. And once we know those voltages, the corresponding magnitude and phase angle, we can then find all other currents, all other losses, etc. Again, all this is being done with respect to a reference. So that's where the difference between power flow analysis and circuit analysis comes in. The injections that, as I was mentioning, are the given load or generator in terms of their power specifications. So given power flow analysis, the power flow module that we will discuss, it will involve nodal injections or bus injections wherein the corresponding load and generator powers would be known. And the assumption involved in power flow analysis, as I have mentioned in the previous lecture, is that it's a steady state analysis. So things or network is not experiencing any change at all in time. In general, thanks to the way our system operates, a high voltage transmission network is a balanced network, and by balanced I mean the corresponding phase A, phase B, phase C voltages and the corresponding line currents, they are equal in terms of magnitude and have a unique angle or property among themselves, which I'll discuss at length as the corresponding time comes in. But overall takeaway is that three-phase AC power networks are often balanced, and under balanced condition we can draw an equivalent single-phase representation for a three-phase network, which if we analyze, we can again transform this back to the three-phase network and get back our actual three-phase values. So in power flow analysis, for sake of understanding, we'll first start the discussion with a balanced three-phase network, which is represented through a single-phase network. The question that often comes in mind is, okay, what if the assumption of balance is not true? Yes, we have dedicated power flow analysis techniques or algorithms for unbalanced networks, which I'll try to explain as the corresponding power flow analysis time comes in. As I have mentioned, generator is represented as a constant power generation source with a specified terminal voltage. There is a reason why this is done. The answer to that lies in the attributes of power networks known as economics. The reason why real power is specified has to do with how the thermal or hydro or renewable energy resource is operating in terms of power generation. So economics is the reason. I'll again explain that as the appropriate time comes in. Transmission lines, they are transposed, balanced, and hence the common nominal pi modeling arrangement is true, with series impedance and half-line charging admittances is present at the ends of the line. All this is coming in because of the nominal pi model. In case these terminologies are new and you are unaware of these topics, please refer to undergraduate level transmission line modeling. This nominal pi model, nominal T model, the discussion of it would become clearer there. Often on high voltage lines, line shunt conductances are difficult to model, difficult to identify, and hence usually they are neglected. We also have transformer, step-up transformer present at the generating station where voltage is amped up, and at distribution end we have step-down transformer where the voltage is amped down. And in power flow analysis, some special consideration has to be made if the transformer is not operating at its nominal tap position. So what do I mean by nominal tap position? The answer to that lies in per unit analysis. I would again request the students to please go through the per unit analysis module before going into depths of the power flow analysis module. In per unit analysis, one of the beauty of per unit analysis is that if a transformer is operating at its rated nominal tap position, then the overall transformer's impedance, be it seen from the high voltage side or be it seen from the low voltage side, the equivalent transformer representation, the equivalent impedance, it remains the same. There is no impact of nominal tap position at all in per unit analysis. So that is what I mean, that if a transformer is operating at its rated nominal tap position, In per unit system, which is the case for power flow analysis, per unit series impedance would remain the same on both the sides, and hence this transformer can be easily modeled as a typical resistive, inductive, capacitive line, the way transmission lines are modeled. Only when the tap position has to be different, which is usually the case because our network doesn't operate at the same load value. In one steady state, the load is appreciable, acceptable, and hence tap positions need not change. But in the other case, in another steady state, if the load values goes up, voltage support has to come in, and that is where the transformers have to operate at different tap positions. Under this different tap position for nominal, off nominal position, the per unit impedance concept no more remains the same, and hence special focus or consideration has to be required, which is precisely what we will see in our next discussion. In fact, our next lecture would begin with the power flow analysis module, which is the first module, and we'll start with the evaluation of bus admittance matrix, which forms a backbone of power flow analysis module. And in this admittance matrix evaluation, we will see as the time comes, how do we consider transformers when they are at their off nominal tap position. Thank you.